All right, so here's our first lesson on linear functions specifically. We've talked about functions. That just means each input has exactly one output. And so linear functions are pretty much anything that is a straight line, with the exception of, remember, our one straight line that is not a function is our completely vertical line. So it's going to be everything except for that, any other line that we could come up with. Okay, some more terminology I just want you to note. We've talked about this before. So it says a race car can travel up to 210 miles per hour. So when you read through the problem, because that's a rate, we're going to write that with the variable y equals 210x. And then solutions are shown in the graph below. So remember that solutions are just going to be any of these ordered pairs here. Okay, so it says, if you just kind of read through here, we know that this is a function because each x has only one y value. It's also linear because it's a straight line, a non-vertical straight line. All right, that's our definition of linear function. So the first thing I want us to do is take these points on the graph and fill in an xy table. All right, and now that we've done that, we want to check what's going to make it linear. So we want to check what's happening between the different terms. And if we look at the change here, for each, so on my x-axis, for each 1 hour, because that's how the x-axis is counting, it's by 1 every time, it looks like the y is changing by 210. And because that is happening every single time, all right, one, this might make you think arithmetic because we're adding the same amount, but it's also going to make the graph linear. So something that you need to take a note of is that when the rate of change is constant, means the same, then the graph is going to be linear, no matter what the rate of change is. So as long as it's the same change between each set of terms, then the graph itself is going to end up linear or looking like a straight line. All right, we happened to look at a similar problem to this the other day when I was talking about arithmetic. So notice here on the x, we're still increasing by 1 every time. On the y, we are increasing every time, but the amount we're increasing by is changing. We've got plus 3, plus 5, plus 7, and plus 9. And so because of that, because this is different, it is going to be nonlinear. And in fact, we're going to learn later on this year, anything that's got x squared in it is actually going to end up being like this U shape, which is definitely not a straight line. It is still a function, but it's not a straight line. All right, so we've talked about how to graph these lines before. I just want to reiterate some of the vocabulary. First of all, when an equation is written like this is in what we call the format ax plus by equals c, and it's important that you know that that is called standard form of a linear equation. And so we're gonna see that a lot. And today we're just going to talk about how to graph that pretty much the same way we've been graphing. First of all, because they don't give you a domain, remember we're going to use the domain of all real numbers. So our graph is going to be continuous when we finish. And so far, the only thing that we've done is made a table of values or a table of solutions. So we've got to, if we're going to graph something like this, we've said before that we need to get y by itself. So I've got negative 4x plus y equals 11. I need to add 4x to both sides, which is going to give me the equation y equals 11 plus 4x, or 4x plus 11. And then we'll use that to make our table of values. And we can pick any x values that we want to. We said it's always good to probably pick a few positives and a few negatives. So I'll pick -1, 0, and 2. I'm honestly just picking a few different values. So we're just plugging in 11 plus 4 times -1. That's 11 minus 4, which is 7. So my first solution is -1, 7. If I plug in 0, I get 11 plus 4 times 0, which is 11. So 0, 11 is my next solution. And then lastly, 11 plus 4 times 2. That's 11 plus 8, so 19. So 2, 19. And then remember, because of how this is written, this should be linear when we finish graphing. So if I go ahead and plot my points, -1, 7, 0, 11, and I'm kind of having to estimate here, 219. This should look, if my points were good, this should have been pretty close to linear. And remember, we're going to connect them with a line because it's continuous, and we knew that because they didn't give us a domain, so we use the domain of all real numbers. All right, so these last two examples are really to show you the difference between discrete and continuous when it comes to real-world examples. So example A, this A part that they have for us here, once you see the problem, you may notice they've already given us the general function. So in your notes, you should probably copy down that we have the general function f of x equals 2x. Now, because this is a word problem, we actually have to consider what domain makes sense. They don't give us a domain, but we can't just assume it's all real numbers. So here they tell us x is the number of DVDs purchased. Well, if we're talking about purchasing DVDs and we want to pick a domain, you could purchase 0 or 1 or 2, or really, this doesn't tell us a limit, so that amount could keep going. You could not purchase a negative number of DVDs. So when we go to graph this on our x-axis, we are only concerned about 0 and our positive numbers going forward. And kind of in addition to that, we're only worried about whole numbers because you can't buy part of a CD. So the general function is f of x equals 2x. We want to, if you need to make a table of values to kind of solve this out, we can. So if you buy 0 DVDs, that means you're going to pay $0. That makes sense. If you buy 1 DVD, you pay $2. If you buy 2 DVDs, you're going to pay $4 because they're 2 each, right? And that pattern is going to keep going. So I'm going to plot those points. So we've got 0, 0, 1, 2, 3, 4, 5, 1, what did we say? 1, 2, 2, 4, and then 3, you might notice 3 would be at 6. So it should be a straight line. And the last question we need to ask ourselves, well, we have 2 more things to answer, I guess. We need to answer range, and then we also need to determine if this should be continuous or discrete. And we said connecting it isn't going to help anything, because if I connect, that means I'm implying that you could potentially buy part of a DVD, and no one's going to buy part of a DVD. So this is actually going to be a discrete function where my range is 0, 2, 4, so on and so forth. And I'm getting that, remember, my range are my y values. So I'm matching each of these points back to their y values of 0, 2, 4, and 6. All right, this second example, we're talking about paying something for, it's $1 for each hour of operation. So when I write my general function, that's just going to be f of x equals 1x, all right, because that's my rate. So when I make my table of solutions, it almost seems silly sometimes to make the table, but if I plug in 1 hour is $1, so that's going to be 1, 1. If I plug in 2, that's 2, 2. And I kind of got carried away here because I didn't actually think about my domain first. So we need to ask ourselves, should it be 0 hours? And I would say, again, in this case, I think 0 is probably a valid domain to include because it is possible that she could rent the stand not for any amount of time if we were talking about like a different day or specific instances. So when I graph this, notice that I'm only going to have these points, 0, 1, 2, 3, 4. I'm counting by ones here. So 0, 1, 2, 2, 3, 3. And in this case, we want to think about, is this continuous or discrete? So when we think about our hours, do our hours have to be whole hours, or could we talk about her renting them for part of the time? And when you talk about time, time itself is continuous. It's not, we don't take just snapshots every single hour, right? We live time in a continuous state. So for this example, we are going to say continuous, which means we want to connect our graph. And then when we say domain this time, we want to say that it's all of our positive numbers. And the best way to say that is that our domain are all of our x values that are greater than or equal to 0. Okay, we can't do negative because that would give us negative time, and that doesn't make any sense. Our range values then are talking about our y values. And if we notice, our y values follow the same pattern. The lowest y value is 0, so that's going to be y greater than or equal to 0.